In this video, I'm going to be going through Groups Sheet 3, and there aren't really that many questions, and the questions aren't particularly interesting. So I'm really going to spend most of the time talking about why I had to write 125 lines just to define the theory of subgroups. In some sense, this gives you some kind of idea as to how how the theorem, how to get a theorem prover, not just to understand a concept, but to make the concept kind of look like the way mathematicians think about it. So we're defining subgroups. A subgroup is so Lean has subgroups, so we call them the my subgroup. And so the idea is that my subgroup G is going to be a new type. My subgroup G will be the type of subgroups of a group G. So how do you give a subgroup of a group G? So here we have G as a type, and we have a group structure on G. So G, that's Lean's way of saying let G be a group. And this new type, my subgroup G, it's a structure, which means that we're going to write down all the lists, the list of all the things that you need in order to have a subgroup of G. And the first thing you need is a subset of G. So set G is the type of subsets of G. Remember, Lean uses type theory, not set theory. So a set is not a primitive object, and somewhere in core Lean, the type of subsets of G is defined. And it could have been called subset G, but it's called set G because I think firstly because set is smaller, and secondly you could think about a term of type set G as being a set of elements of G, if you like. So a subgroup of G is a subset of G, and that subset is going to be called carrier, which is not the kind of word that a mathematician would use. And the whole point of the next 100 lines after this is we're going to be removing all references to this word carrier. So a subgroup of G is a subset of G which satisfies some axioms. So the subset of G is currently called carrier, which is kind of annoying. And its full name is going to be my subgroup.carrier. Look, you can see it here. Check my subgroup.carrier there. And it takes a subgroup of G and returns a subset of G. And we don't really want to be talking about carriers, but we're stuck with them now. So here are the axioms for a subgroup expressed in terms of this sort of carrier thing. And the way subgroups work, the way substructures of a structure typically work, is that a group has axioms, but we don't care about the axioms. For example, one of the axioms of a group is associativity, right? But you don't want to say, oh, the subgroup has to be associative as well, because if you think about it, that's sort of obvious, right? The multiplication of the subgroup is just multiplication on the group. And so if the group is associative, then the subgroup will automatically be associative. So where do the axioms for subgroups come from? They come from the structure of a group. So a group is, what is a group? It has a multiplication, it has an inverse, and it has an identity. And that data part of a group is where the axioms come for a subgroup, because the idea is that that data has to somehow all get inherited by the subset. And so the axioms are, you don't want the subset to have a new identity. The identity of the group has to be in the subset. So that's called one mem. It's called one mem prime for reasons we'll see later. And mul mem, the idea is we've got two things in the subset, then their product needs to be in the subset. And finally, if X is in the subset, then its inverse needs to be in the subset. So there's one axiom per piece of structure that we have on a group. And that's the definition of subgroups. And now you see, what we really need to do now is to make subgroups kind of work the way that we think they work. So for example, we would need to prove that here's a silly thing. How do we know that if two subgroups are equal? Two subgroups are equal if the underlying subsets are equal, right? That's somehow a kind of a completely obvious thing, but that's the sort of theorem that we're going to have to prove. But actually, Lean we have a computer program that proves it automatically. So if we tag my subgroup with the ext attribute, then Lean automatically, something kicks in, and it's in my subgroup.x. That won't have been there before. If I check it up here, right? Check my subgroup.x, I get an error. It says I've never heard of that. But under this line here, if I check it, I still have an error. So I was wrong. It's because I've got it's because I've got the underline. Let's try that. There we go. Let's do that experiment again. Yeah, it wasn't there before, and it is there now. You see. So for example, this X says if two subgroups have the same underlying subset, then they're the same subgroup. So this is just the kind of nonsense thing that a mathematician would never think about, and doesn't have to think about, because this is all sort of being generated automatically. But this is the kind of boilerplate that has to go in whenever you make a new definition. So we've defined my subgroup, and now let's go into the my subgroup namespace, and let's prove some theorems about my subgroup, each of which will be sort of completely trivial, and somehow a mathematician might say, well, we've proved them already or something, or they're not worth proving. But in a theorem prover, one has to prove them. So what are we doing here? So this says let G be a group and let H be a subgroup. It's worth observing, just while I'm here, if I check G, it says that G is a type, right? Because G is, G is a group, right? So it's a set with some structure. But a subgroup, you also think about a subgroup as a set with some structure as well. But in fact, it's not. Look, if we check H, H is not a type. H is a term, even though I've written it with a capital letter. H is a term of type my subgroup G. So this is just a sort of a subtlety that's going on here. The idea is, if we want things to be in H, if we want X to be in H, then we don't write X colon H, because H is not a type. H is a term. H is a subgroup of G, and a subgroup of G is a subset, and subsets are not types in Lean, because the types are the things that are playing the role of a collection of things, and sets and subsets are different things. They're somehow, they're different things. They're terms, not types. So G is a type, but H is a term. It's sort of worth pointing this out. So now there's something called mem. There's has mem, which is this is a notational type class. The idea is that A is an element of B is supposed to make sense, using the usual maths notation there. So what right now, you see, here's the problem. Let me give myself, let's put those variables up here so we can have them now. We can do this. We can check is A in H, right? There. If A is an element, if A is a term of type G, we could ask if A is an element of H. And Lean says, I've got a clue what that means, because H is not a set, right? H is a subgroup. It's not a subset, and we haven't defined what it means for a term of type G to be an element of a subgroup. So this would make sense. There, H dot carrier is the underlying subset of H, and so we could write it like that. And this is just the kind of thing that we don't want to be writing. We want to write mathematics the way it's written in the textbooks. We don't want to distinguish between the subgroup H and its underlying subset, and that's what we're being forced to do here. And so we're going to make an instance of has mem G my subgroup G, which just means it once we've made this instance, it will make sense to have a term of type G, i.e. A, and a term of type my subgroup G, i.e. H. It will make sense to ask if A is an element of H. And the definition is, we can see the definition here. We could perhaps put A there. What does it mean to say A is an element of H? It just means A is an element of H dot carrier. So if we move this check down to here, there. Now the point is that this should now work there. So A is an element of H now works, which is good because that's what a mathematician wants to write. And similarly here, this sets up a coercion from subgroups to subsets, because sometimes you want to talk about H as a subset. So if I check, let's do this up here. H is a subgroup of G, but if I want to check H as a subset of G, then I get an error here. It's complaining that H has got type my subgroup G, and it wants to have type set G. But this line here creates a coercion from subgroups. This is all very technical stuff. You might not need to know this stuff. I'm just showing, I guess what I'm showing you is the pain that goes with any definition. Every time you make a new definition, there's a certain amount of pain that comes with it. And I'm showing you the pain now. So now H is a subgroup of G, but the idea is we can also consider H as a subset of G. And lean just reminds you, there's that little up arrow there, just reminds you that you're secretly applying a function, the function that takes a subgroup of G to the underlying subset, which is H dot carrier. So finally, so that's what all the boilerplate is about. If you weren't remotely interested in that, apologies. Oh, so there's more. Sorry, there's still more boilerplate. This lemma says that that if H is a subgroup of G, then G is an element of the underlying subset of the subgroup, if and only if G is an element of the subgroup. And this is true by definition, because the definition of G is in H is G is in H is defined to mean G is in the underlying subset. So the proof of this is REFL. And now finally, the last bit of boilerplate. Remember I had these one mem primed, mul mem primed, and inv mem primed, because all of these things mention carriers. So we're trying to move away from carriers completely. You see this simple lemma here says G is in H's carrier if and only if G is in H. And if the simplifier ever sees G is in some carrier, it will just simplify it away and write G is in H. So this is what's going on here. Let me remind you what H dot mul mem says. Have H is H dot one mem primed. There. This is the original axiom we have for our subgroups, and the axiom says that one is in H dot carrier, right? But what we want is, we don't want to have carriers here, there, and everywhere. We want to be talking about one is an element of H, so we write one mem, one is an element of H, and that's by definition equal. You see, this is exact H, right? They don't, they're not syntactically equal. The goal is what we want. H is something which is syntactically equal to the goal. Sorry, it's not syntactically equal to the goal, but it is definitionally equal. And so exact will work because exact works up to definitional equality. And the idea is that one mem is just a tidier, this is what we can just, there we go. Look, let's just check H dot one mem primed. The idea is that looks a bit ugly, really. One is in H dot carrier, but H dot one mem that we have now is one is in H. You see, that's the sort of thing that mathematicians would expect. But because when we define subgroups, there was some carrier involved, we've had to so mul mem and inv mem are just the same. Mul mem and mul mem primed are definitionally equal, but they're syntactically not equal. And mul mem and inv mem are sort of more beautiful than mul mem primed and inv mem primed. So there's a rather long overview of, you see, every time you make a new definition, it comes with a cost. And that's an example of the kind of cost we have to pay. So this is what you need to know, is that there's now a new type called my subgroup G, and if H is a term of that type, then H is a subgroup of G, and we have these three basic facts, which now look, there's no mention of carriers, they now look like how we would expect them to look. I think maybe I'll just stop here. I think maybe I'll do the proofs in another video. I think that's quite enough technicalities.